I became interested in lipids by the early 70s when we studied blood platelet aggregation that is well inhibited by prostaglandin E1 or PGE1. At that time, the inhibition of platelets to prevent thrombosis by the elevation of their cyclic AMP content was a target, and PGE1 was added to this purpose. Considering that diamogamma-linolenic acid or DGLA could be usefully converted into PGE1 within platelets, we looked at the possible platelet inhibition by DGLA. This worked in vitro, but failed in vivo when we tried to increase platelet PGE1 through the intake of gamma-linolenic acid, the precursor of DGLA, even in population at risk for increased platelet function, such as elderly people and diabetics. The findings in the late 70s by Bang and Dierberg that thrombosis may be prevented by the long-chain omega-3 fatty acids, EPA and DHA, prompted us to study the effect and metabolism of those highly unsaturated fatty acids in platelets. Indeed, both fatty acids compete with the generation and action of the arachidonic acid-derived thromboxane that induces platelet aggregation. However, high concentration of EPA and or DHA may induce oxidative stress, which activates platelet aggregation, especially in elderly people and diabetics, where the level of oxidative stress is already elevated. Interestingly, we showed that EPA and or DHA used at less than 1 gram per day, considered as a moderate dose, paradoxically decrease oxidative stress and lower platelet activation. Another project was to study the double lipoxygenation of DHA and of its precursor alpha-linolenic acid into conjugated trienes called poxytrines, especially protecting DX from DHA. We found that these compounds inhibit both platelet cyclooxygenase activity and thromboxane-induced aggregation. On the other hand, in the 90s, we started to be interested in the compartmental metabolism of DHA. We found that equal amounts of DHA are present in blood as non-esterified form and esterified in lysophosphatidyl-choline or lyso-PC-DHA, both forms being transported by albumin. Interestingly, DHA in lyso-PC-DHA was around tenfold more efficiently taken up by the brain, a preference not found with other organs. This observation was also valid for oleate and arachidonate. This has been recently corroborated with the discovery, by others, of a specific protein recognizing lyso-PC expressed by the blood-brain barrier and responsible for such an uptake. After that, we came up with the idea of acetylating position 1 of lyso-PC in order to avoid migration of DHA from position 2 to position 1. This provides acetyl-docosahexaenamyl PC, a structured phospholipid named acido-PC. We now see that the acetyl group of acido-PC is mobile enough to acetylate several targets, resulting, for instance, in the inhibition of tumor intestinal cell proliferation, as does aspirin. We now try to combine our approaches dealing with various DHA derivatives and the preferential brain uptake of fatty acyl containing lyso-PC. We hope this will contribute in the development of DHA-related lipidomics, especially fluxolipidomics.